Hi everyone, I'm Alex Wine, and this is joint work with David Gamarnik and Akosh Jagannath. I'll be talking about random optimization problems. So for example, finding a large clique in a random graph, finding a good solution to a random K-SAT formula, or maximizing a random degree p polynomial over the unit sphere. Note that in contrast to some statistical questions, here there is no planted solution. And we'll be interested in, first of all, what is the typical value of the optimum, but also what objective value can be reached algorithmically, meaning with a polynomial time algorithm. And we'll see that in some cases, it appears to be computationally hard to reach a particular objective value. And in these cases, the goal will be to understand why this is, and ideally to do this in a unified way that applies to many problems all at once. So here is a concrete example. Given a sparse Erdős-Rényi random graph with constant average degree d, find a large independent set. So it's known with high probability that the maximum independent set will have a particular size, but algorithmically, we only know how to find an independent set of half that size, and this is achieved by a simple greedy algorithm. Karp famously asked whether a better algorithm exists, and to this day we do not know one, and in fact, evidence has begun to emerge suggesting that no such algorithm exists. This is because the independent sets of size larger than alg are clustered in a way that defeats certain algorithms such as Markov chains. More concretely, we now know that the class of local algorithms can find independent sets of size alg, but no larger. And here, roughly speaking, a local algorithm allows each vertex to decide whether or not it should be in the set based only on its local neighborhood in the graph, along with IID random variables attached to the vertices. Here is another example called the spherical p-spin model, which can also be thought of as the problem of maximizing a random polynomial over the sphere. So here we observe a p-tensor with Gaussian entries, and the goal is to find a unit vector maximizing this tensor form. So we know that with high probability, the true optimum will be a particular constant. And algorithmically, we know how to achieve some other constant. And this is strictly smaller than the true optimum when p is at least 3. Note that when p equals 2, this is just a simple eigenvector question. And in this case, we know that a certain class of iterative schemes called approximate message passing can achieve the value alg, but no better. Okay, so what's missing here? Well, I'd like to think about how to give the best evidence that there are no better algorithms than the ones we currently know. Prior work has ruled out certain classes of algorithms, but do we really expect these to be optimal? Well, one troubling fact is that AMP is actually not optimal for the related problem called tensor PCA, which is like the p-spin problem, but with a planted signal. We would also ideally like a unified framework for lower bounds that applies to all sorts of problems at once. And so in this sense, local algorithms are undesirable because they only make sense for sparse graphs. And the solution we propose in this work is to give lower bounds against a larger class of algorithms, namely low-degree polynomials. And this is a class of algorithms that contains both local and AMP algorithms, along with all sorts of other things, including the best known algorithms for tensor PCA. Okay, so like I said, we're going to study a restricted class of algorithms called low-degree polynomials. And these are just polynomials with m inputs and n outputs, by which I really mean a tuple of n different polynomials, one for each output. and each of them is a multivariate polynomial with m inputs in the usual sense. And so we should think of the input to this polynomial as just being whatever input we're given in our problem. So it could be a graph represented as one variable per edge. And the output will just be whatever the output to our problem is supposed to be, which could be a binary value for a decision problem, or in our case, it will be a vector that encodes the solution. So for instance, the indicator vector of a independent set. And here when I say low degree, you should think logarithmic in the dimension for reasons that I will justify later. So why do we care about this class of algorithms? Well, one reason is that it captures many existing frameworks. So if we imagine that our input encodes a matrix, well, one thing we can do using low degree polynomials is power iteration. So starting with, say, the all ones vector, we can multiply this by our matrix a bunch of times to get an approximation of the leading eigenvector. We can also do approximate message passing for a constant number of iterations, or a local algorithm with a constant radius. And crucially, we can also do any of these applied to some pre-transformation of the data. So maybe we want to take our input, use that to build some other matrix whose entries are each constant degree polynomials of the input. And then we could do power iteration on that matrix. So this allows us to capture certain non-trivial spectral methods, such as the non-backtracking walk matrix used in community detection, or the tensor unfolding method used for tensor PCA. Another reason to care about low degree polynomials is that they are already well studied for problems that have a planted signal. So this was initiated by this influential line of work on the sum of squares hierarchy and is further discussed in this survey article. When I say a planted problem, one canonical example to have in mind is planted clique, where the goal is to distinguish between two distributions. So I give you a graph, which either is just an Erdős-Renyi random graph, or it's a random graph with a planted clique on k vertices, and your goal is to decide which it was. And for a certain values of the clique size, this problem is believed to be computationally hard, even though it's statistically possible. So for a whole bunch of different planted problems coming from high-dimensional statistics, we now know that, first of all, the best-known polytime algorithms are captured by low-degree polynomials, specifically by either spectral or AMP algorithms. And one reason for this logarithmic degree is because this is how many rounds of power iteration are needed if your matrix has a spectral gap. And on the flip side, we also know how to prove that low-degree polynomials fail in the conjectured hard regime. So this gives some concrete evidence that the problem is hard, and in particular rules out algorithms like spectral and AMP and so on. So this gives quite a nice general framework for explaining why these types of problems are sometimes easy and sometimes hard. And the goal of this work is to extend this framework to non-planted problems, like the ones that I discussed earlier. You might have also heard of some other frameworks, like the sum of squares method or statistical query model. But for these, it's not so clear how to extend them to the non-planted setting. I should also point out that there are some limitations to the class of problems for which we believe low-degree polynomials are optimal. For instance, in XORSAT, low-degree polynomials are beaten by Gaussian elimination. But somehow Gaussian elimination is not such an interesting algorithm for statistical problems, because it's very brittle to even a small amount of noise in the input. So let me now present our main results. So if you recall the spherical p-spin model from earlier, we are able to show that no low-degree polynomial can optimize all the way to the global maximum. A bit more formally, we are considering a polynomial that takes as input this whole tensor and outputs a vector. And we're saying that no low-degree polynomial can succeed with high probability, where succeed really has two different components. First of all, the objective value needs to be near optimal, where here I'm using h to denote this objective value. But also the output of the polynomial needs to be normalized correctly. So it needs to be almost a unit vector with high probability. And similarly, for the maximum independent set problem, we are able to show that no low-degree polynomial can reach a certain objective value that's in between opt and alg. Or more formally, we're considering polynomials that take in the graph as input and output a vector. And no such low-degree polynomial can succeed with high probability, where success now is defined as follows. So we want this output vector to be the indicator vector of an independent set. And so we require that most of its entries are either close to 0 or close to 1. And if I take the entries that are close to 1, these encode a near independent set of the desired size, where we allow for a couple of errors. In follow-up work, it's actually possible to improve this to the optimal threshold. So we now know that low-degree algorithms can achieve the value alg and cannot achieve 1 plus epsilon times alg. So let me try to now explain the idea of the proof. I'll point out that for problems with a planted signal, it's usually possible to prove lower bounds against low-degree polynomials by a direct linear algebraic computation. But here, for random optimization problems with no planted signal, we need a very different approach that will combine two different ingredients. So first of all, we'll use stability of low-degree polynomials, which roughly means that the output of a low-degree polynomial doesn't change too much when its input changes a little bit in some sense. And we'll also use something called the overlap gap property, which is a structural property of the solution space. And the version that we'll use here is most directly inspired by this line of work here. Okay, so I'm going to sketch the proof for the independent set problem. So let's start with the overlap gap property. So this states that with high probability, if you draw a random graph from our model, then there is no instance of a particular structure. So what does this structure look like? It consists of two independent sets called S and T in the graph, such that individually they are both large. They have this target size, where here phi is just this value that we saw previously. And furthermore, their intersection size is exactly phi. So two large independent sets that have a specific overlap. And how to prove that no such structure exists is actually a simple first moment calculation. You just compute the expected number of such structures and show that it's extremely small. So actually that was just a warm-up, and the real version of OGP we need is a bit more sophisticated. So we have to consider a sequence of correlated random graphs. And so the first one is just a random graph like before, but now we resample the edges one by one in some fixed but arbitrary order in order to get this sequence of correlated graphs. And the ensemble OGP states that still there is no occurrence of this forbidden structure, where S and T are large sets that have a specific intersection size. But now S is allowed to be an independent set in any one of these graphs, and T also is allowed to be an independent set in any one of these graphs, possibly a different one. So let's now see how to use this to show that low-degree polynomials fail. So let's assume, on the contrary, that we had a low-degree polynomial that outputs large independent sets. And let's again consider this sequence of correlated random graphs. And we're going to apply our function f to each one of these in order to get an independent set. And the first fact we'll need to use is that since y0 and ym are independent graphs, it turns out that the first and last independent sets need to be far apart, so they cannot overlap very much. This is another fact that can be shown using the first moment method. And then crucially, we'll use a stability property of low-degree polynomials. So with some non-trivial probability, there are no big jumps in the polynomial's output. And what this means is that the second independent set needs to be quite close to the first one, and so on. But this actually contradicts the overlap gap property, because if we need to go from this first set to this last set in sort of a continuous way, well, that means that somewhere along the way, we must find an independent set whose overlap with the first one is this value phi, which is forbidden by the overlap gap property. Let me just conclude by making a few comments. So I said earlier that you could improve this to the optimal threshold. To do this, you have to consider forbidden structures that depend on many independent sets instead of just two. This type of idea was first used by Raman and Virag to prove the analogous result for local algorithms, but the details here are quite different. For the p-spin model, the proof of the analogous OGP property is not just a simple first moment calculation, but actually relies on some fairly deep results from spin glass theory from these papers here. For the p-spin model, we also prove lower bounds against the Langevin dynamics algorithm, which is like a continuous time Markov chain. And the way we do this is because this algorithm has many of the same stability properties that low-degree polynomials do. Also, this work can be seen as addressing a larger meta question about what are the connections between different heuristics for hardness, such as low degree, OGP, sum of squares, etc. So here we've shown that a certain variant of OGP implies low degree hardness. And looking forward, we hope that in the future, these types of ideas can be used to understand all sorts of different random optimization problems, and hopefully establish the low-degree framework as a useful general purpose tool for understanding computational hardness of these types of things. That's all. Thanks for your attention.